So yeah, thanks for coming out. Thanks to the CNN News for this opportunity. I think the only person who's ever called me talented is probably my mum, so I feel honoured now. And I think I really wish I was a sort of a fly on the wall when you guys are coming up with these nicknames for us. It's a pretty fun thing to do. Okay, so a bit of a fun title here, but we make polymers, and we're a polymer chemist, so we think we can solve all the problems with polymer chemistry. And so I'm going to go through a few things with what we do in our group. It's quite a broad program in some of the areas we work in, but specifically, we're going to talk about at the end a bit of the catalyst system, which is a polymer particle where we have these active sites that we can perform catalysis, and these are inspired by active sites of enzymes. So we've been asked to think about our journey and just share this with you guys, and it's a fun thing to do, I would guess. And I think this picture sort of sums up my journey. I don't really have a Nicolas Cage moment, but it's more like this sort of just various paths to go ahead, and the opportunities that I've had, I've really set this path, and it's more about just me deciding at the time where that opportunity would lead me. So I'm going to take you back to where I was born, and this is the map of Australia. So this is Melbourne down here. We're at the southeastern point here of Australia. Famous for a few things. Probably what I would like to say is the best game in the world, which is Australian football. So this is the home of Australian football. It fits about 100,000 people. I have a pretty deep-seated relationship with football. I was actually born on a Saturday afternoon, which is when our grand final was played. I was born during the grand final. So that's like basically your Super Bowl. It was my dad's team was playing at the time and lost terribly, so I don't think he was having a very good day. And ever since, I actually don't barrack for the same team. I actually barrack for his arch rival, which is probably a story for another time. But also, we are famous in Australia for the best coffee in Australia and the best food, the best nightlife in Australia. There's no one else to claim otherwise here, I don't think, so I'm going to keep with that. So I moved around a little bit as a child and went to Canberra. And so this is a great city because it's home of politicians. And politicians are great, really great. And I know so because I've asked people, lots of people, and they all think what I think. So that's my attempt there to humour there. I figured I wasn't Australian, so I might be able to try to get away with that. So I'm not American, so I might be able to try to get away with that. Anyway, so moving on from Canberra. So this is where my scientific journey started, which is at Melbourne University. And it's really with these two people here who have really set me off on this journey, this opportunity to explore polymers. And so I want to tell you a little bit about these guys. So they run a really broad research program, I would say, and it's really what I do now, I would say, is because polymers can solve all our problems. And in particular, I'm talking about Dave Solomon. So Dave I think he's 78 now or 79. He still comes in 1 or 2 days a week to the university. And he's holding their polymer banknotes. And I've got a couple of examples here, which is our money, which is a bit technicolor and a bit crazy here at the moment. You guys who haven't been to Australia might not have seen it. But this is made out of plastics, and he led the lab that made this. So it's multi-layered material. It's made with security features. It's got a feel. It's got durability. And he was in a lab for basically 20 years in a top secret lab. He couldn't tell anybody to develop this. And so when I arrived in their group, of course, this was after the polymer banknotes was around, so he could tell us all these stories. So group meetings will often go with quite interesting stories about how he accomplished this impact. And I think I wanted to say that as well, because he's not somebody who's published science papers and nature papers, but he's somebody who's made a really great impact, really huge impact especially in Australia, but now it's actually out to 20 other countries in the world as well. Scientifically, he's also done some significant impacts as well. So he's the inventor of nitroxide-mediated polymerization as well, which has had a huge impact. Pretty much every department in the world does some sort of, every chemistry department in the world will probably do some sort of controlled radical polymerization. And he's written a book on that. And his group, after he left, also invented raft polymerization as well. So a huge impact. So basically, I just wanted to give a feel for the breadth of polymer research, and I wanted to sort of take that theme through my talk a bit. So after my PhD, I was sort of waiting. My wife was finishing her degree, so I wanted to let her finish before we moved overseas. And Frank was nice enough to let me do a short postdoc in his lab. Frank runs things a little bit differently. And I wouldn't say it's a broad program, but it's really quite a focused program. And I learned a lot from Frank because of that, and how you can focus on a really specific goal and and work as a team to try to get towards that goal. And so I've learned a lot from Frank. And then I've made the trip across the Pacific, which I also did on Saturday, and which means I'm probably a bit red-eyed right now still. But so we made the trip across there with Craig, and so as you can see here, Craig's sort of wearing his flag on his chest here, his rugby union jersey here. This is the picture of the group which I made him take on a silly camera which spins around and takes a camera, of course, on a polymer film as well. So that's the group. We've made some really great friends here and lifelong friends. And again, the research that Craig's group does is really quite broad, from polymer solar cells to therapeutics and to some catalysts as well, to sort of pure polymer chemistry. So I guess that's the sort of the theme that I'm going for. So then we went back to Melbourne here. So this is my group. It's a great group of people. I would like to just thank them now, and I'll thank them again later as well. But these are guys that really drive the chemistry in the group and the creativity in the group, and it's a really fun place to be. So I could have drawn it like this. I feel like I could have drawn it like this as well. So this path has almost gotten me on a circle now. And even more so, as you heard before, now I'm actually heading to Canberra again here. So in November, I'll be moving to Australian National University and moving the group there. So I feel like I'm on a circle now. I'm not sure if I can get off this circle, but again, taking opportunities as I go, and it's been a fun journey. Okay, so why are plastics fantastic? So I just wanted to sort of give you a little bit of the idea, the concept of how we design our polymers. So this is just a cartoon version of a polymer. Here's a polystyrene unit. So this is ubiquitous in many applications, but it has no functionality here. It's just an aromatic ring. It doesn't have the chemistry that performs some sort of function. So to give you one example here from my group here, we have designing really functional, highly functional materials. So in this case, we have a temperature responsive polymer, but also a polymer with an amino acid on the side chain here. So we have amino acid functional polymer with the retention of the R group of the amino acid. So we're looking at a bio-inspired approach to make new materials to try to do some of the things that proteins can do. So that's just sort of the concept, I guess. We're looking at the molecular engineering of our units of our polymer to then perform some sort of function. And so that means we're performing lots of functions and making lots of different polymers. So I just want to give you a bit of a snapshot of some different programs that we're doing. So we're trying to control the nanoparticle shape of nanoparticles. We think this is important for different polymer therapeutics. So different shapes of nanoparticles are shown to be quite important for drug delivery. We've become interested recently, probably serendipitously, about hydrogen sulfide donors. So we're making hydrogen sulfide donors. We think it's a really cool molecule that we haven't really figured out all the biological implications of what H2S actually does. We're doing a bit of 3D printing. So here, again, we're trying to make a printable ink that can then do something after it's been printed, not just an innate object. And in this case here, we have a butterfly printed. It's a bit useless, but the material inside it actually is self-healing. So we could cut off this butterfly's wings and put it back together again. So in Australia, we have a lot of things in the ground. So we dig them up and we sell them. So we have a bit of a program that we're actually looking at making polymers that interact selectively with different valuable ore, and we can then purify that from the unwanted material. So we have a program there with chemical engineers to do this, so selectively interacting with polymers. So again, controlling the monomer units to do some sort of function. And I want to talk to you about this one today, and this is enzyme mimics work. So it's really looking at enzymes and what trying to get away from their disadvantages and how we can put them into polymers. So I'll go into some bit more details here. So enzymes, it's pretty easy to talk to a group like this of why enzymes are important. They literally build our DNA, they control our largest organ, and they're getting our nutrients from our food. So that's a pretty easy motivation to sell here. So enzymes also have lots of applications. I don't want to go into all of them. If I was in Australia, it would definitely be time for a beer, I think, but I'm not, unfortunately, so I'll have to wait a couple more hours. But we'll talk about detergents. So this whole program has really been started from detergents and the industry coming to us and saying, can we replace enzymes from detergents because they're unstable, they don't last as long as they should, we have to protect them, there's lots of issues there. could we even get to cold water washing instead of heating up to 37 degrees? So that's the motivations here. And enzymes, I always say that enzymes' greatest power is also their weakness. So they have this beautiful tertiary structure, but if you lose that, then you lose the function. So we're trying to build stable mimics that can do the similar chemistry, but without losing their function, so increasing the operating range. And how do we do this? We look at the enzyme and break it down into various properties to see if we can then mimic these properties. So we look at the active site, we look at the environment around the active site, and also how it also lowers the transition state for the catalysis. So we started with this by basically going to a biochemistry textbook and looking up the active site, and then it had a picture like this, which was a serine protease, the catalytic triad. And we basically said, can we make a molecule that looks like this? And we did. I'm not going to show you the results so far, but I'll show you the chemistry, how we made it. But we've made this one molecule with the 3 groups of the catalytic triad in this one molecule, which we could also then conjugate onto polymer surfaces. So I've got the chemistry. I don't want to go into details, but it's just really say that we have a scalable method, simple method. In the one step, we can get all these functional groups into the one molecule. We then conjugate that onto a polystyrene support for our catalysis. And that's actually really quite important to control the environment around this catalysis. So I just wanted to show you the snapshot of what this looks like. The enzyme has this perfect arranged active site. We have these active sites throughout this polymer particle. And really, the environment around this, it's one thing to get these active sites in the one molecule, but we've found actually it's even more important to control the local environment around its active site to improve catalysis. So the future for us in terms of this project, we were really looking at the active site. We're talking with computational experts. What's the perfect arrangement of this active site? Can we then make that synthetically? I just went on to the environment around the active site. We really want to control this. It's had much greater effect than pushing atoms around, so it's really important to us. We've also had our next generation of catalysts is looking at transition state binding and how do we also lower that. And the bottom point here is more of a grander scientific goal, I would say. And can we make this one polymer with sequence control, which will then fold like a protein does to then perform some sort of catalysis? So with that, it's my last slide for acknowledgements. I really want to thank my group in particular, all my collaborators. And one person I haven't mentioned really yet is at Kostel. He's at Unilever, and he's basically was at one of those streets telling me to come down the street, because he was one that challenged us to say, can we create an enzyme mimic? So without him, I'm sure I wouldn't be here today. So thank you.